we go to the next slide. Is this one? Which is going to next? Oh, that one. Okay. So basically, the whole talk is the introduction to the modern architectures of the three platforms we supported. And that is a high-level comparison. And because of that, in our three code generators, a commonality and the difference. And then a lot of the code gen details, I'm going to talk about it. So the agenda is the chip comparison and core comparison, ISA, and our flow of code gen, and ISA implications on binary size, performance, execution time, path length. Addressing mode for the code gen, mainly for the load store instruction or memory operand. And addressing mode for branch and call, and the condition code for the loop, and if, whatever there, and a register allocator. Binary encoding, instruction scheduling, and reassociation optimization. Going to the next slide. Chip comparison, I mainly refer to the top line of the most current chips on the three architectures, namely x86 Skylake, and the power is Power 9, and Z is Z-. Nowadays, when you talk about the chip is equal to socket, equal to processor, equal to CPU processor. In the past, it's not the same, but nowadays it's basically the same. All these three processors are fabricated on 14 nanometer process. Skylake is by Intel's 14 nanometer process. And Power 9 and Z14 are fabricated by the Global Foundry 14 nanometer. Global Foundry actually is IBM's previous facility in Fishkill. Is acquired by, we sold it to Global Foundry. On the same chip, you compare the Skylake, Power 9, and Z-. The core count, Skylake is up to 28 cores per chip, and the Power 9 is up to 12. Z14 up to 10. And you look at the L3 caching. So this slide all contain the chip level resource, not a core level private resource. So L3 is typically a chip shared resource. Skylake contains 38.5 megabytes of L3 cache shared by all the 28 cores. Power 9 is private, is 10 megabytes per core. Although the L3 cache can be shared among the cores, but it's slow. Because it's private, you have one cache line handed to your neighboring cores. L3 took 20 cycles. It's not that fast. Z14 is 128 megabyte L3 cache shared by all the cores. And memory channels, memory connection. Skylake has 6 channels, and the Power 9, 8 channels. Z14 is 5 channels. Now, on Power 9, the 8-channel memory connection can be connected in 2 ways. For the low-cost machine, is connected through DDR, double data rate connection. That's the industry standard memory connection. For the enterprise machine on the same chip, it can be connected through the DMI channel, the direct media interface channel. The DMI, the buffered memory connection provide close to 2x of the memory bandwidth, but it slow down the memory, if you have the buffering chip there, the memory latency is around 15 to 20 nanoseconds longer. So you look at the memory bandwidth per chip, per socket. Skylake is the theoretical memory bandwidth is around 118 or 117 gigabytes per second. But really you can pull to use it is probably around 90 gigabytes per second. On power, the 8 channels, if you are going DDR, is going to be 153 gigabytes per second. That theoretical max. Really, you can use it probably around 120. But if you are going to buffer the memory, the theoretical is 230 gigabytes per second. You probably can use around 190 gigabytes per second. The Z14, the number is secret. Maybe Julian knows. But you probably can deduce it from the Power 9's buffered memory is around how much it is. And Z is always buffered, and X is always DDR. That's my understanding. And give you a perspective how much this memory band is okay, is good for the running. If you look at the HPC, the high performance computing code, it demands a lot of memory bandwidth. The Skylake per core actually can pull around 40 gigabytes per second. So that 90 gigabytes per second is probably only good for 2 cores. So you can imagine if running that kind of code, your 26 cores sitting idle, you cannot do anything. Only the 2 cores can pull in the bandwidth. So in this perspective, you can see the P9 and the Z14 is more scalable for that kind of workload. And the connection for the L3 cache is shared versus private. There's a performance implications here as well. I have been going through these performance issues with many customers between X and P. For if you're running single-threaded on the chip, then that single thread for the X case, it can use close to 40 megabytes of cache, L3 cache. But on power, you can use 10 megabytes. So sometimes the performance is the customer saying, hey, power running slower. But my answer to them, you are not buying the machine to run single thread, right? I stop here. Any questions? Okay. So the core comparison and ISA comparison. That's per core. Each core for simultaneous multi-threading is equal to hyper-threading in x86 land. Skylake is up to 2 SMT threads. And now SMT thread means hardware thread, means logical CPU on AIX. AIX basically name each hardware thread as a logical CPU, and on Linux, each hardware thread is termed as a vCPU. So it's all this thing, terminology is the same thing basically, depending on which platform you are seeing the terminology. Virtual CPU actually on AIX means another thing. Okay. On x86, each core can run up to 2 SMT threads. Power 9, each core run up to 8 SMT threads. And the Z is up to 2 threads. The ISA kind of landscape is instruction length on x86 is 2 bytes to 15 bytes. Power is 4 bytes, always. Z is 246. Addressing mode, you can see x86 is very powerful there. The B plus X multiplied by S plus immediate, that means base address register plus index register multiply a scale, the element size, plus a displacement immediate. Plus there's another addressing mode for IP relative to the instruction pointer, basically relative to the current instruction, and your offset going to be a certain amount offset. So it's IP relative addressing, that two mode of that there are a lot of sub mode. The B plus X multiplied by S, and you can combine flexibility to have a lot of mode there. But you look at power, the instruction set there are only 2 modes for the load and store instruction. You either going to base address plus index register, or base plus a displacement of 16-bit. Only that. Z is in the middle, is close to the X addressing mode, base plus index plus displacement, and IP relative as well. Branching and core, x86 provide a 32-bit distance, branching distance. And for indirect core, they are using the GPR to contain the address, so the branch is GPR based. On power, the C there, it means conditional. For conditional branching, power only provide 16-bit worth of branching distance. For unconditional branch, it's 26-bit. For indirect core, you need to use a special register, not GPR. So on power is called LR and CTR, link and counter register. On Z is the branch, relative branch is 32 bits multiplied by 2 distance, because their instruction is always 2 bytes, 4 bytes, 6 bytes, is multiple of 2. And indirect branch is GPR based. The register set, x86 is 16 GPR plus 32 vector. And power is 32 GPR plus 64 vector. And Z is 16 GPR plus 32 vector. Condition code, x86 is E-flex. Power is 8 condition registers. Z is the CCW. Cache, I will not, this is just for information, because the cache architecture and the memory consistency, I'm leave it for the part 2 talk. Any questions? So the flow of code generation. In our code compiler, the code generation basically going through instruction selection and register assigning and people optimization and finally binary encoding. There used to be 2 stages between the register. Before there's a pre-RA instruction scheduler, and after the register assigning, there's a post-RA instruction scheduling. That right now is all disabled, and it's disabled for a good reason, basically, because all the cores nowadays is all out of order, deep out of order machine. So the hardware itself provides scheduling capability already. Instruction scheduling actually didn't provide much performance benefit, but it will take a lot of compilation time. That it is not good for JIT environment. Any questions? Okay. So for the instruction length implications, the X and Z, they are typical binary operations, arithmetic operation instructions are destructive. Destructive in a sense that the example there is A equal A plus B. Then the A is destructed. If you want to keep the A value for future reference, you need to copy the register, or you need to later to rematerialize it. So you probably see more register copy instructions on X and Z. But I know Skylake microarchitecture actually optimizes this copy instruction. The register copy instruction is actually not issued to the pipeline. They can be finished in a stage of register renaming. You just rename it, it's finished. And also X and Z allow memory operand for non-load store instructions. On power, load store instruction, the memory operand can only used in load store instruction. For any arithmetic instructions, is register based. This has binary size benefit because if you look at the instruction of increment the memory operand by 1, on power typically you need to load it and add 1 to that loaded value and store it. You need to use 3 instructions, and the encoding is 12 byte. But on X, you probably only need the 2 byte instruction to do the inc. So that binary size benefit is obviously is there. And now, what is path length? Path length basically how many instructions this is a dynamic sense. How many instructions you need
to finish a piece of work.
That's called path length. That potentially including loop, right? So it's different from the binary size. The binary size is a static sense. So because they have a memory operand for non-load store instruction, have the path length benefit as well. The 3 instruction on power versus 1 instruction on X or Z. However, that doesn't mean power take more time to execute the add, the increment, because the memory operand instruction internally actually is cracked into 3 micro-op anyway. So from a pipeline issue point of view, the 3 micro-op need to be issued there versus power 3 instruction issued there. And the x86 instructions are mostly of 2-operand format, so they are mostly destructive. They have 3-operand format for the new instruction FMA. FMA means floating, multiply, and add. Floating, multiply, and add, you need 3 sources anyway. You need register A multiply register B plus register C. And the result needs put into a register. So you have 3-operand format, it's still destructive. Z architecture is a mix of 2-operand and 3-operand. I saw the newer instructions are of 3-operand. But the older 2-operand instruction is destructive. The 3-operand probably is non-destructive. But I didn't go through the percentage, how many instructions are destructive, how many are not. And the power is mostly of 3-operand, so it's mostly non-destructive. But for the VSX, the vector FMA is 3-operand, so it's destructive. Any questions? No question, okay. Addressing mode implications on instruction selection. Here the limitation is mainly on power because the addressing mode is either base plus index or base plus displacement. And the displacement is limited to 16-bit. 16-bit basically you negative 32K, positive 32K. And there is no architected IP register. You cannot refer to the IP register. So there is no IP relative addressing. So give you an example. Typically you are iterating over a Java array. On power, you need to use more instructions for sure, because for our object model, you have a object header, 8-byte or whatever, and then you have an index. So what you need to addressing a particular element, you need to add the index. First, you need to multiply something shift on an index, plus the base, and plus the header. So it's quite a few instructions to go to addressing it. Unless loop strider kick in, and you can have the internal pointer. So basically the base register can point anywhere in the object in the middle. And then you don't need that long sequence to calculate the address. In the past, we certainly have a proposal for BiDi object model that will help the power for sure. What the BiDi object model, basically the Java object reference point at the start of the data, not at the start of the header. So the header is in a negative offset of your object reference, and the data is in a positive offset of your object reference. But this is in the past this is problematic for Z architecture, because the immediate offset is always positive, is unsigned data. So it cannot address the negative. in order to address the negative, you need to use the index form. You need to move a negative value into a register and using the index form to address it. So that's the problem there. But nowadays, the new Z architecture allow both negative and positive offset. So it's probably a BiDi object model can be revived, resurrected. But there's still probably some implication here. I believe the Z architecture for the negative offset addressing is a 6-byte instruction, right? Not 4-byte. So it has the implications of bigger binary. Accessing stack frame. The stack frame, it can be more than 32 kilobytes. I have seen this, especially when escape analysis will end up allocating a lot of objects on a stack. Then the stack frame becoming bigger than 32K, that certainly is a problem for power, because power you have the stack register plus 16-bit offset, and that only addressable up to 32K. When you're bigger than 32K, what happens is you have a performance issue here, performance impact, because our stack frame addressing binding is late. It's at the very late stage. So you even don't know which, in the instruction selection phase, you don't know which item is offset more than 32 kilobytes. And at the binary encoding time, you found, hey, this thing is more than 32 kilobytes offset. Then what you want to do? Because you already passed the register assigning stage. Now you need to evacuate a register to calculate the offset. That evacuation of the register certainly has performance implications. You evacuate the register typically to the negative offset of your stack, and then you calculate the address, and you addressing the stack, and then you load it back that register. That is a lot performance penalty there. And also for accessing static variable and a constant address, something like a J9 class and a J9 method. In this way, the IP relative addressing is really handy. But on power, there's no IP relative addressing. So, but we have a lot of register. So we, in Power CodeGen, we dedicate one register. In 64-bit mode, we dedicate one register as the pseudo talk. So what is talk? And what is talk is the in the ABI, in the traditional ABI for the ELF or XCOF, they have something called GOT or talk. GOT means global offset table, and talk means table of constant. So basically what it is an area. This mainly is for position-independent code and shared library for the benefit of shared library, because you don't want to modify your instruction sequence in the shared library to encoding the particular global address. If you modify that, then your shared library cannot be shared by many processes. So what they do is the ABI basically have a GOT or talk. And in the GOT and talk, you put the global address there, and you are using IP relative addressing to address that GOT or talk to load the global address, constant address. But on power, we don't have IP relative addressing. So we dedicate one in a C or whatever environment, we have a dedicated register to point at the talk. And then you can similarly doing the IP relative addressing. And in JIT, we have another, because we have so many registers, so we have dedicated another register to point at the pseudo talk. Now, pseudo talk basically is similar to the talk. It containing a global, containing a J9 class, J9 method, and a floating point, a 1.0, whatever, that kind of constant in that pseudo talk, and then using that pseudo talk register to reference the global constant. However, if you have a pseudo talk overflowing, then you have trouble. Then you need to revert back to a long sequence of materializing the address. In particular, for a 64-bit mode, you use 5 instructions to encoding the long 64-bit address. And then when you are using pseudo talk, you also have the peak side invalidation. When class unloading is happening, you need to take different actions. So that is the particular things on power code gen. That's the different things here. So any questions on this? Yeah. Yeah, the question is the pseudo talk is for per method or globally for the whole JVM. Yes, the pseudo talk is the global for the whole JVM. And the pseudo talk is, we have a hash table in the pseudo talk. We know which one, for example, Java object class pointer is in index of 32. Then globally, wherever the JIT code is running, if they need the JavaLang object class, it just access the 32 offset of the pseudo talk. So it's a single pseudo talk for the whole JVM. Any other questions? So branch and call and trembling. So you keep in mind on X, the branch distance can be 32-bit. So that basically up and down 2 gigabytes. And on power, your conditional branch is only 16-bit. So that up and down 32 kilobytes. For a unconditional branch and a call is 26-bit. That is up and down 32 megabytes. And Z even bigger is up and down 4 gigabytes. And now the implication here is limitation is also mainly on power, but it can happen on other on X and Z as well. For within a method, that typically conditional branch. So do you have enough the branching distance for conditional branch within a method? Power it happened. It happened relatively frequently. You don't have enough branching distance within the method for conditional branch. The biggest method compiled I have seen in PMR is 300 kilobytes actually. So you can only jump up and down 32 kilobyte is not enough. So what happened here is we have a pre-encoding phase scan to identify the potential long branches, and then change the identified potential candidate of long branch. We will turn, if you are doing a branch of if greater, then we turn it into a branch if less than or equal. Reverse the branch direction, and then the real branch is using the unconditional one. Unconditional one can go up and down 32 megabyte. That's enough. So basically, then you're assuming there's no method compile requiring more than 32 megabyte. That typically is a safe consumption assumption. Now, going to, do you have the branching distance for a direct call, static call, for example? This can happen in the past on all platforms. Because in the past, the code cache is allocated separately, each piece by piece, as you run. So you can imagine you have a code cache, a piece of code cache is more than 4 gigabyte away from your previous code cache. Now, in that case, even though it can address up and down 4 gigabyte, then it's still not enough. On X is only up and down 2 gigabyte. So, but in I think it's since Java 8 or Java 7.1, the code cache that's a big code cache is something. Big code cache is preserved there, 256 megabyte, and then every code cache is carved one piece out of that preserved 256 megabyte, piece by piece. In that case, X and Z will not have the problem of not enough branching distance. But on P, it still can happen because your preserved area is 256 megabyte. P can only jump up and down 32 megabyte. So it's still not enough. On all platforms, this can happen for helper call because the helper is in the shared library, and how far away shared library from your code cache, that is platform dependent and runtime dependent actually. So if not the 2 gigabyte, whatever, not enough, then you still need the bridging help from the trembling. So what is the trembling? Basically, you have a tiny piece of code to bridge the call. You don't have enough branching distance. So in your code cache, your branch is jumping to the trembling, and trembling is responsible to transfer your control to the long distance away callee. But it create an illusion that you are calling to the callee directory. Okay, next slide I can show you what the trembling look like. And trembling actually is saving encoding space. You can imagine in your code cache you call to method full a lot of times, and you cannot reach full. If you are not using trembling, you need to encode the long sequence in many places. But you have a trembling, you have a single trembling sitting in your code cache. Every call just jump to the trembling. Basically, trembling is the surrogate of your calling in your current code cache. Also, it require trembling for atomic patching purpose. If you have method of recompilation, and you need to patch your call to the new target, then if you directly encode your call in your mainline sequence, then you cannot patch it. In multiple instructions, you cannot atomically patch it at one go. But for trembling, you can. Any questions? Okay, so next slide, basically the binary encoding and the late creation of trembling. Binary encoding is you always need to keep in mind we have the dynamic instruction patching can happen. You need dynamic code patching can happen for a lot of places in a JIT environment. For the data method and the class resolution, basically the data method and the class are unknown at the time of your compilation. You need to resolve it. Then you resolve it by instruction patching. So you need the instruction patching for that. Compilation and recompilation is require patching as well. No of guard invalidation is patching. Class loading, unloading, and pre-existence optimization can trigger patching. And the compilation failure also can trigger patching. So for instruction patching, because it is a relatively more complicated topic, it have I-cache coherency implications and CMOD X specification, basically concurrent modification, and again, that is for the part 2. I will talk about more about that. But for this talk, instruction patching, basically the requirement is the atomic behavior. So for atomic behavior, at least you need to align your instruction on the right boundary for the atomic patching to succeed. So this is basically is a hardware specific requirement on instruction alignment. On power is relatively simple because every instruction is a 4 byte. So it's automatically is aligned and you can patch it simple way. But because there are different instruction lengths on X and Z, then you probably need to take care of the alignment of what you are patching. And now for trembling. Trembling is created on demand because most of the time, even on power, it's not many applications generate more than 32 megabytes of binary. So typically the 26 bit of the branching distance is enough for most of the time. For example, for a typical Liberty day trader run, the binary generated probably around 14 megabyte to 15 megabyte. But for SPECJ Enterprise 2010, it's typically 28 megabyte to 30 something megabyte. And in that case, occasionally you can have the trembling is required. So trembling in that scenario, our trampoline is created on demand. Only when you do instruction patching, you found, oh, I cannot reach the target. Then at that time, you are requesting the trampoline to be created. Now, for that to always succeed, because this is a runtime behavior, you cannot allow later creation of trampoline to fail. If you fail that, then your whole runtime fail, right? That is not allowed to fail. So the space for each potential trampoline is preserved. Basically, you preserve the memory, and then later on, you always can grab the space to create your trampoline. Now, trampolines still need to be patched for recompilation. Now, the question on whether trampoline can be atomically patched, modified in place, that is platform specific. On X and Z, yes, the trampoline can be modified in place, but on P, no. So trampoline, what trampoline look like is on a green portion. The trampoline, basically, you compose the address and then jump to the address. Jump, I need to emphasize, is jump to address, not call the address. Because you call the address, your return address is for the callee, the return address is going to be after the jump, and that is not where you want to return. Because your return address should be on the initial branch, instruction branch to the call to the trampoline. So in this sequence, you should not basically trashing your return address. The return address already established for the initial call to the trampoline. So trampoline can only use jump. You jump to it, it's not a call. It will not create a return address again and trashing your initial return address. Also, it needs to be aligned for patching. And as I mentioned, X and Z can do the patching in place because they have the 8-byte address in the branch instruction somewhere. You can do the patching in place. But P is multiple instructions with using the 16-bit displacement things to calculate the address, and then you cannot patch it in one go. So what happened on Power is we have a temporary trampoline. We create a temporary trampoline and redirect the initial call to the temporary trampoline to jump to the new target. And the temporary trampoline will be cleaned up on the next GC when the world is stopped. Okay, any questions on this? Yes. The question is where to put the temporary trampoline. So in each code cache, you have 5, right now is by default 5% of the code cache is cut out for the trampoline space. In that 5%, you have how many, I don't remember how many it is, probably 64 or something we reserved for temporary trampoline. Is typically in real life, we have never seen more than 2 or 3 is used. So it's enough already there. Any questions? Yep.
You just said 5%. I was wondering how many potential trampolines you have based on the number of directions. Yeah, fixed amount.
the 5% that's the past story, the historical reason. The trembling, how big the trembling is, I think on X and P and Z, 16 byte. 16 byte is the trembling. P is 24 byte, and I don't remember. I think it's up to 24 byte. So the capacity for the trembling area is calculated from power size estimate. You 24 byte, and for a typical code cache, 5% allow you more than the typical method compilation is on power is 2 kilobyte to 3 kilobyte or something. You calculate it is basically enough. And by the way, on AMD 64 in the past, they have the peak, the interface call can create a trembling, and in the past they have a bug or somewhere. We do overflow the trembling area occasionally. I think that's fixed. And nowadays, you even don't need trembling because they preserve 256 megabyte code cache. Any more questions? Condition code and condition register. The difference between XZ and P is on X and Z, arithmetic instructions set the condition code by default automatically, whether you want it or not. On P, arithmetic instructions don't set any condition registers by default unless you ask for it. There's a instruction form, it's called a record form instruction. It's 1 bit in the instruction. You can ask for the condition status for particular instruction. And on power there are 8 condition registers in total architecturally. For compare instruction and conditional branch instruction, you can designate which CR to use. And for record form instructions, it's a specific CR is implied according to the instruction type. For example, for integer instructions, is CR number 0 is implied. For floating point, the CR6 is implied. And multiple condition registers allow parallel evaluation of conditions. This is a capability right now. We didn't take advantage of it. Only in one case in our current code generation for the loop. When you have a loop back branch, typically there is a sync check there as well. So we use 2 condition registers, one for the branch control, another for the async check. That's the only place I know we use multiple condition registers. And actually, for parallel evaluation of conditions, multiple condition register is performance benefiting potentially. If all the conditions are unpredictable, you use multiple condition registers, actually it's performance benefiting, because if you don't have multiple condition registers, you need multiple conditional branches, and each one is unpredictable. You have potential prediction miss, and you suffer the multiple miss penalty. But on power, you can combine. There are CR logical instructions to AND or X or whatever the instruction bit, the condition bit, then you can land it on a single instruction. Single branch instruction, conditional branch instruction. So if you suffer a precision miss, you suffer once, not suffer multiple times. For X and Z, I suppose E flag and CCW are renamed as well, because if you are not renamed, you will serialize on it most of the time, because every time you by default setting the E flag and CCW, then you not renamed, you basically serialize on it. Any questions on this? Yes. Yeah. On power basic register allocator, need to assign 8 condition register as well. Any more questions? So registers and global register allocator and local register allocator. So in CodeGen, we're typically dealing with virtual register. And you have the real register is called architected register. And a register assigner is to manage the life cycle of virtual register and assign the real register to the VR. And also there's a register renaming or register buffer or reorder buffer, whatever is in modern architectures. That is basically another thing of register. CodeGen mainly dealing with virtual register and the real register, architected register. But there are actually hundreds to thousands of renaming registers in each core. And that is aggravated by transactional memory, actually. For example, on Skylake, per core is close to 350 registers. The GPR side is 180-something renaming buffer, and the floating point side is more than 160. On Power 9, you think about it, it's not surprising at all. You have 8 SMT. Each thread, the architected register is 96 already. You have 32 plus 64 vector. And you multiply by 8, that is close to 800 architected register. Plus renaming is going to be more than 1,000. And plus transactional memory. Transactional memory, you need to keep the old register. So it's even more, basically. Now, for starting early on x86, they already have partial registers. The AL, AH is overlapping with the EAX, whatever, right? Yeah, that's the partial register problem. And with the introduction of vector register, this even happens more frequently. The x86 has the XFM register, YMM register, ZMM register is all overlapping. And the power is similar. Is the floating point register is overlapping with the vector register. It's only partial of the vector register. And the Z floating point is partially overlapping with the vector register as well. There's a performance implications here because your non-overlapping portion, how is it defined in ISA? Basically, it's undefined versus unchanged. There's a performance implication here or pipeline usage implication here. For example, on X, you have the ZMM register, the 512-bit register, and it's partially overlapping with the 128-bit XMM register. Now the architecture need to define the non-overlapping part is undefined or unchanged when you are using the XMM register, the lower portion. If you have, in the past that you have implementation problem here, performance problem here, if you didn't carry the non-overlapping portion with you, then later on you need to combine things together. But if the instruction set that defined it as undefined, then you are free. You are free to go because it's undefined anyway. And also is relevant to how the pipeline is used. If it is unchanged, you need to carry the whole 512-bit with you in order for it's not changed. But you carry that over, basically imply you need to use the wider pipeline to push the instruction through. And I can tell you on power is almost always undefined. The non-overlapping portion is undefined. So the hardware implementation is free to go, basically. And global register allocator, this is different. The overall framework is the same among the 3 code generator, but is configurable and parameterizable to each code generator. Basically, how many real registers you can be used for global register candidates, and which real register are most favorable for the candidate. And this is configurable in each code generator because it is up to each code generator, but platform specific to decide which real register is most favorable. All this information is carried to code generation through the GL regdep nodes. And for local register allocator, the status of the real register set is controlled through register dependency condition. So that is used to honor the global register allocator request, also guarantee no spill for certain code regions, and enforce the linkage convention. Also for ISA special cases. For example, for x86 divide remainder, they are using specific register. And the P and Z, the GPR 0 have special meaning. You need to do this condition register as well, condition dependency as well. Any questions on this? Okay, my time is okay on that. I need to go faster, I think. Linkage convention and the JI direct. JIT private linkage convention basically is the JVM is own ABI. So naturally you have question, why not just using the system ABI? There is historical reasons. We are using, I think the most simple answer is that in the past, we are doing the compilation on the same, we are doing compilation, JIT compilation on the same stack, same thread of application thread. So if you are using the same stack for the native code and Java thread, you potentially for every Java thread you need to have a big stack. So in the past, basically we separate. So native stack is native stack, Java stack is Java stack. So the compilation probably cannot cause the thread stack to be that bigger for implication for the Java stack. Now you have a different stack, so you have a different linkage already. The linkage basically is how real registers are used, which are volatile, you can modify, which are preserved, and which are reserved. Reserved, basically, you cannot touch on it. And how arguments are passed to your colleague, and how value is returned, and what the stack frame shape look like. That is the linkage. And also, your argument passed, if you pass on stack, you have load hit store performance implications. So what is load hit store is you have a older store and a younger load to the same memory. And if your load is issued later than the store, and you check the store queue and you hit the store, that in that case, store forwarding need to happen, and typically is going to be rejected, and then store forwarding on X and Z. The store forwarding is fast, and sometimes it can reject it. You also suffer performance there. On power, typically load hit store penalty is higher, and the store hit load is when you issued out of order, load is issued first, store is issued later, and store check the load reorder queue hit the load, you need to reject, and that is load hit store penalty. And also, this can also happen when you short-circuiting complicated calls without shrink wrapping. Basically, you have saved a lot of register, but you return right away because you have a condition, oh, something is a null pointer, I'm going to return right away. And that return, you need to load, you need to restore all the preserved registers. And there are a lot of load hit store happen there. And JNI direct call, basically this is the bridging the linkage convention difference between the JIT private linkage and system linkage. You need to bridging that difference even on a different stack. If you can dispatch JNI through interpreter or helper call as well, but the overhead is very significant. You can imagine how significant it is because you need to copy the argument from the Java stack to the native stack, and you need to have a meta code to set up. You need to decoding the signature to know is a floating point argument or integer argument or whatever there, and that decode take time, and the shuffling of argument take time, and you need the metacode physics, metacode sequence to set up the register. For example, you need to name the group GPR3 to contain the first argument on power. That kind of thing is overhead is high. And the JNI direct call itself has a lot of overhead. You need to building the stack frame to anchor the call, and release, we acquire VM access. This all including atomic update. And after your call, you come back, you need to free the reference frame. Before the call, you need to prepare for potential GC. And at the end, you need to tear down the stack frame. It's pretty expensive. And right now, I think we have a better, lighter mechanism in the work. Possibly is better. Any questions? Okay. Instruction sharing and reassociation. Instruction scheduling, basically you have the constraint of the same semantic of instruction sequence, and then you're moving them around to fit the pipeline better. And not much benefit with the current crop of deep outer order execution engine. I have examples in the next page. Reassociation opt is much more beneficial, and I have the example later as well. What is the reassociation? Basically, you take advantage of certain algebraic property and to reorganize the expression evaluation. Any questions on this? And this page. So I'm going to describe why is the instruction scheduling is not that beneficial on outer order machine. So on the generate code column and the scheduled column, I have a basic machine model here. Is a load instruction is a 5-cycle latency, and arithmetic instruction is a 6-cycle latency for floating point, and it is typically true. The arithmetic instruction is a 6-cycle, and the load is a 4 to 5 cycle. And the example is currently is pretty popular that idiom for machine learning, for whatever there is the matrix multiplication or vector product sum. That is the typical idiom here. So you hear the example is you basically square each element and pass together, put it in X environment, in a variable. So if you unroll this loop twice, the generate code look like you load AI and square the R1, put it in R2, and add R2 to X. And load I plus 1 and square it and add it. If you are not out of order, and although you're pipelined basically means if the next instruction is independent of the previous instruction, it can go. But if you're dependent, you cannot go. So for this instruction, the load instruction is issued. The result will come back in 5 cycles, and the next instruction of multiply R1 to R1, and because it's dependent on the load instruction, so load is issued, the MAU cannot go. You need to wait there for 5 cycles, although you are pipelined, but you are not out of order. So you can roughly calculate it. That sequence with that model, it will take 29 cycles. But if you scheduled, you go into the scheduled column, you move the load, the 2 load together, and 2 MAU together, and the 2 add together. In this case, you can go load and then load AI in the first cycle, but in the next cycle, load I plus 1 can go because they are independent. And there, you need to wait a few cycles. Once the R1 come back, the first MAU can issue. And the next cycle, the R3 come back, the next mile can go. And you can calculate it. This, for that pipeline, the model is around 23 cycles. So that is a 20 to 30% benefit because of scheduling. But on out-of-order machine, you feed this instruction, the generate code instruction, into the out-of-order machine. It will execute it as the scheduled one anyway, because it can out of order, can be out of order. Your load, mile cannot issue is hold there, and add cannot issue hold there, but the load the fourth instruction can go. It will eventually it will look like the schedule anyway. So that's why the scheduler is not providing much benefit because of this. However, reassociation is going to help this. I have the reassociated unroll 8 times. You can imagine the execution is going to look like 8 load, 8 mile, and the few add there. So the reassociation is when you do the 8 load, 8 mile, and you're coming back, you are not going to sequentialize on the X register. You are going to add R2 and R4 together first, going to a new register. Basically, you reassociate the thing, not going to depend sequentially on your target register. So R2, R4 add together, R6, R8 add together. You have 4 such add is independent of each other. It can go. And after that 4, you can have 2 independent Y and Z together, and M plus J together. That can go in parallel as well. And eventually, at the last moment, you are sequentialized on X. You X plus T1 and X plus T2. So if you assuming there are 2 pipes for each type, same latency model, you unroll it 8 times. If you're only doing as the scheduled one, 8 load, 8 mile, and 8 add sequentialized, that will require 59 cycles. But if you reassociate as the reassociated column showing, you calculate roughly 35 cycles. That is almost twice better. And this is our JIT compiler right now cannot do this, but is sitting on Andrew's radar somewhere. Okay. Any questions? Okay. So it's almost on time, right? Any questions? Then probably my part 2 talk is about the cache architecture and the memory consistency model. Okay.
Thank you. So let's give a round of applause to Julian for doing such a great job on a very complicated topic. So we'll end here today. If you have any more questions, let Julian or me know. Like we were talking about earlier, he will deliver the second part, so hold your interest for a month. If you really want to know early, we can also reschedule if you want the talk earlier, but right now it's scheduled for next month's talk. And if you have something that you would like to share, like I was talking about earlier, let me know, and we can schedule that in as well. So thank you all for coming, and hopefully you learned something today. Thanks.